We are looking at enhancing the secret messages program from the YByte Python curriculum available at www.ybyte.in. In that pursuit, let's look at yet another substitution cipher called the Beaufort Cipher. Now, previously we looked at this thing called a Vigener Cipher, which is essentially a generalization of the Caesar cipher, which we looked at in the class. The idea is that Beaufort Cipher is in fact yet another variation of the Vigener Cipher. Hence, every letter gets a different shift, and this is dictated by a list which we call as a key. Just like before, just like in Vigener Cipher, the key can be of any length and can have numbers going from 0, 1, 2 until 25, since there are 26 letters in the alphabet. However, the way we apply the shift is different, and it's quite interesting in Beaufort Cipher, and that's why we look at it in this video. There are many descriptions available on the internet, but I thought a couple of examples will make things very clear. That's what I'm going to do. Let's look at a few examples to see how does this cipher actually work. Let's say I want to encode a string which is called abracadabra with this key, which is 15, 18, 21, 24. Now, like I said, every letter is going to get a different shift. In fact, the way I'm going to compute the cipher text letter is very, very interesting. I'm going to look at the key. I'm going to look at the position of every letter inside the letters. For example, A is 0, B is 1, R is 17, C is 2, and so on and so forth. I'm going to find out the key minus the position of this letter. So 15 minus 0 is 15, and it turns out letters 15 is P. So basically A becomes a P. Next I go to next letter, key is 18. I do 18 minus 1, 17. As we already saw, 17 is an R. Next I go to 21. 21 minus 17 is 4. I get letters 4, which is E. I get 24. 24 minus 0 is 24. I get a Y. And that's how we form the coded string. Notice here each letter is getting a different shift, and if it just turns out that the key is exactly this sequence. For example, if the key also was 0, 1, 17, 0, 2, 0, 3, 0, 0, and so on and so forth, my coded text is going to be all A's, because really what I'm doing is I'm computing key minus the position of the letter. So that's how I compute the cipher text. Now you might wonder what happens if my key is smaller than, let's say, these positions. Now this example was carefully chosen so that that situation never happens, but really that is not a problem, because we can see this in the next example. Let's say here I have a key of 1, 2, 3, 4, and my letters are from the higher side of the alphabet. So for example, say turn right. Notice 1 minus 19 is minus 18. This looks odd, but remember in Python, I can index lists with a negative index. So all I need to do really is to say letters minus 18, and that is perfectly fine. So that's what I'm doing. So 1 minus 18 is minus 18. 2 minus 18 is also 2 minus 20 is also minus 18. 3 minus 17 is minus 14. 4 minus 13 is say minus 9. This one nothing happens. I go to 2. 2 minus 17 is minus 15. What I'm trying to get at is that the same exact algorithm can be used regardless of whether my resulting index is positive or negative, because basically indexing from the negative number is just means indexing from the right side. However, just to be consistent with all the other codings, just keep in mind that when I have x of minus 1, that's in fact same as x of 25. We have seen this before because that's really the last element. But that's also same as x of minus 1 plus 26. So which means that if you look at this in the literature, many times you will see this written as mod of 26. That's not a problem. We are going to also continue with that. The code that I'm going to follow is quite simple. I'm just going to modify my Vigener Cipher. I'm just going to compute I'm going to compute the new index, like I said, based on the key minus the index. Now, once again, this I is taking care of, this modulo operation is taking care of the fact that key is being applied in, let's say, certain length and repeatedly applied. I just find the new index, and that's really all. This modulo 26, let it be here, doesn't really matter because even negative indexes also. So I come in here to my code here. I just duplicate this piece of code, which was for the Vigener Cipher, and I copy it and I just rename this into, let's say call it say BEAUFORT Cipher, Beaufort Cipher. Now remember, all I need to do really is that I need to compute the new index by finding out the difference between the key and the previous index. Remember, IDX contains the previous index, the position of the letter, and this list key contains the keys that we are using. This modulo operator is making sure that, just like in Vigener Cipher, it just makes sure the key kind of repeats, right? And that's really all I need. When I run this code, if I were to now try this, let's say I say XB is say BEAUFORT, say cipher. Let's just try the same string, abracadabra, dabra, and let's also use the same key so that we can compare 15, 18, 21, 24. If I did this, my XB is indeed what I thought it would be. It's PREYNSSOBV. Let's just make sure it's indeed exactly what I had imagined it to be. Let's try one more example. Let's say I did, say turn, let's say right, like we were doing earlier. This time around, let's use the key, let's say 1 2 3 4, because that's what I had done in my example. So I say, for example, key is say 1, say 2 3 4, and if I look at my XB, it's IIMR space LVYUJ, and I guess that is exactly what I had found earlier when I did it sort of manually, right? So you see this working very simple. It's interesting to note that the same code is going to work for both encoding and decoding. We'll see the decoding in just a moment. We'll explain to you why the same logic works, but just to let you know, the same code is in fact is going to work. I hope you found this interesting, and in general, if you think this way of learning is fun, do look at our website because we have many, many, many such activities that can make programming very, very interesting. Take care. Thank you so much. Bye bye.